What space discovery still doesn't have a real explanation? Story 1. So here's the situation with dark matter, which sounds like it should have been solved by now, given how long we've known about it. Roughly 27% of the universe's total mass energy content is made of something that doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any detectable way, and yet absolutely positively exists because its gravitational effects are written all over the universe in ways we can't explain any other way. We first noticed the problem in the 1930s when Fritz Zwicky calculated the mass of the Coma cluster of galaxies from how fast its galaxies were moving. They were moving too fast. The visible mass wasn't enough to hold the cluster together gravitationally. It should have been flying apart. Then in the 1970s, Vera Rubin measured how fast stars at different distances from galactic centers were orbiting and found the same problem. Outer stars were moving too fast for the visible mass. Something invisible was providing extra gravity. Decades later, we've mapped dark matter's distribution across the universe through gravitational lensing. We've built underground detectors cooled to fractions of a degree above absolute zero, trying to catch dark matter particles colliding with ordinary atoms. We've found nothing. Directly, zero confirmed dark matter particles in any detector. Here's the part that's genuinely unsettling. Dark matter might not be a particle at all. Some theories propose it's something fundamentally different. Primordial black holes, modifications to gravity, something we don't have a name for yet. The most popular particle candidate, WIMPs, have been searched for extensively and not found. The second most popular, axions, are being searched for now. 27% of everything in the universe is stuff we've never touched, never seen, and might not be able to directly detect. We only know it's there because of what it does to everything around it. Story 2. In 1998, two independent teams of astronomers were measuring distant supernovae, Type 1 supernovae specifically, which function as standard candles because they all explode at roughly the same brightness. The idea was to track how the universe's expansion was slowing down due to gravity. Both teams expected to measure deceleration. Both teams found acceleration instead. The universe isn't slowing down, it's speeding up. Whatever is causing this acceleration has been named dark energy, and it accounts for approximately 68% of the universe's total mass energy content. It is, by a wide margin, the dominant component of the universe. It is also the thing we understand least. The simplest mathematical description of dark energy is Einstein's cosmological constant, a term he added to his field equations and then famously called his biggest blunder when he thought the universe was static and it wasn't needed. Turns out it was needed, just for different reasons. The cosmological constant corresponds physically to something like the energy of empty space itself, vacuum energy, having a non-zero value that pushes outward. When quantum field theory tries to calculate what the vacuum energy should be, it gets an answer that's off from the observed value by somewhere between 60 and 120 orders of magnitude, depending on how you do the calculation. That's not a rounding error. That's the largest discrepancy between theory and observation in the history of physics. We have a name for it. We can measure its effects. We can put it in equations where it works. We have no idea what it actually is, why it has the value it does, or whether it's constant or slowly changing. The dominant component of the universe is a mystery with a placeholder label. Story 3. This one should be straightforward. The Hubble constant, h, describes how fast the universe is expanding. Specifically, it says how fast distant galaxies are receding from us per unit of distance. It has units of kilometers per second per megaparsec. Measure it. Done. Except two completely different methods give two completely different answers, and both methods are solid, and both have been checked and rechecked for years, and the answers keep not matching. Method 1. Look at the cosmic microwave background, the oldest light in the universe, the afterglow of the Big Bang, and use our best cosmological models to extrapolate the expansion rate. This gives approximately 67-68 km/mpc. Method 2. Look at nearby distance ladders, Cepheid variable stars. Type 1 a supernovae and measure the expansion rate directly from observations of nearby galaxies. This gives approximately 72-74 km SMPC. The difference is about 10%. That sounds small. It isn't. Both measurements have been refined over years. Both now have error bars tight enough that they don't overlap. The statistical tension between them is above 5 sigma, which is the threshold physicists generally consider definitive. Either one of the methods has a systematic error that nobody has found despite years of looking, or the universe genuinely behaves differently than our standard cosmological model predicts, meaning there's physics between the early universe and now that we're missing. Completely new physics, a fifth fundamental force. New particles in the early universe, something that changed the expansion rate at some point in cosmic history. Physicists have been arguing about this since the measurements got precise enough to create the problem. They're still arguing. The tension is real and still unresolved. Story 4: Odd radio circles. Giant perfectly circular radio structures found in 2020 that don't correspond to anything visible in 2020. Astronomers using the Australian Square Kilometre Array Pathfinder telescope were doing a radio sky survey and found something nobody had ever seen before. Giant, faint, perfectly circular structures emitting radio waves. So large they dwarf entire galaxies, with diameters of hundreds of thousands to millions of light years. They called them odd radio circles, or ORCs. The specifically strange things about ORCs, they're only visible in radio wavelengths. Point optical telescopes at the same location and you see nothing, or just a faint galaxy near the center, with no obvious connection to the circular structure. They're not glowing in X-rays or infrared, just radio. And they're almost perfectly circular, which is unusual in a universe that generally produces messy, asymmetric structures. They're also rare. We've only found a handful. This could mean they're genuinely uncommon, or it could mean our sky surveys just haven't been sensitive enough to find more of them. The theories proposed range from plausible to genuinely creative. One leading hypothesis: they're the shock waves from enormous energetic events at galactic centers, maybe a past burst of star formation or black hole activity, propagating outward through intergalactic space like ripples in a pond. Another: they're viewing angle effects of something we already know about, like radio galaxy lobes seen from directly in front. Another: some kind of collision or interaction between galaxy cluster winds. None of the theories has been confirmed. We don't have enough examples to statistically test them against. Arcs were discovered in 2020 and remain unexplained in 2024. A new category of cosmic structure found, and what's making them is still unknown. Story 5: Diffuse interstellar bands. 100 years of unexplained absorption lines in starlight, and we still don't know what's absorbing it since the 1920s. Astronomers have known that something in interstellar space is absorbing light from distant stars in very specific patterns, specific wavelengths, that don't match any known atom or simple molecule. These are called diffuse interstellar bands, or DIBs, and there are now over 500 of them cataloged. 500 specific signatures of something absorbing starlight in the space between stars. For a century, we haven't been able to say with confidence what most of them are. The absorbers are clearly some kind of molecule or molecular structure in interstellar dust clouds. The diffuse part of the name indicates they're spread through the interstellar medium rather than concentrated in one place. But the specific molecular identities of most DIBs are unconfirmed. This matters because interstellar chemistry is one of the frontiers of understanding how the building blocks of life are distributed across the universe. The interstellar medium contains surprisingly complex organic molecules, amino acid precursors, ring structures, long carbon chains. Some of the DIBs may correspond to these complex organics. Some may be Buckminster fullerene, spherical carbon molecules, which has been confirmed for a couple of the bands. But the vast majority remain unidentified. The challenge is experimental. You need to produce the candidate molecule in a laboratory, measure its absorption spectrum precisely, and compare it against the astronomical observations. Many candidate molecules are extraordinarily difficult to isolate and study in the laboratory conditions that would match interstellar conditions. Something is out there, spread through the space between the stars, absorbing light in specific patterns. After a century of trying to identify it, most of it is still unknown. The universe between the stars contains chemistry we haven't read yet. Story 6: Dark Matter is the famous missing mass problem. But there's a second, less famous missing mass problem that's arguably more embarrassing. We're missing a huge chunk of ordinary matter, baryonic matter. The stuff made of protons and neutrons, the same stuff you're made of. Big Bang nucleosynthesis, the extremely well-tested process by which the early universe made hydrogen, helium, and lithium, predicts how much ordinary matter should exist in the universe. The cosmic microwave background provides an independent measurement that agrees precisely. The universe should contain a specific amount of ordinary, normal matter. For decades, when astronomers added up all the ordinary matter they could find, in galaxies, in galaxy clusters, in gas clouds, they came up significantly short. About 40–50% of the ordinary matter the universe should contain was nowhere to be found. Not dark matter, ordinary matter. Protons and neutrons just missing. The resolution, partially found, still being confirmed, appears to be the WIM, the warm-hot intergalactic medium. Enormous filaments of diffuse, extremely hot gas that connect galaxy clusters in a cosmic web, too hot to emit visible light, but detectable in X-rays and ultraviolet. Recent observations have started finding this gas, and it appears to account for a significant fraction of the missing baryons. But the accounting isn't fully closed. Some of the missing ordinary matter has probably been found in the WIM. Whether all of it is there, and whether we've correctly measured what the universe should have, is still being worked out. The universe made ordinary matter in a specific quantity. Finding all of it is still an ongoing project. Story 7: On October 15, 1991, physicists at the Fly's Eye detector in Utah recorded a cosmic ray particle entering Earth's atmosphere with an energy of approximately 310 electron volts. To put that in context, a single subatomic particle, almost certainly a proton, was carrying as much kinetic energy as a baseball thrown at about 100 kilometers per hour. From a single proton, moving at essentially the speed of light, this broke known physics in a specific way. There's a theoretical limit on how energetic cosmic ray particles can be when they reach Earth from outside our galaxy, called the Greisen-Zatsepin-Kuzmin limit, or GK limit. When ultra-high energy particles travel through space, they interact with photons of the cosmic microwave background radiation and lose energy. The GK limit describes the maximum energy a particle can have after traveling cosmological distances. The oh my god particle had significantly more energy than this limit. Either it came from somewhere extremely close, or it came from somewhere we can't identify, or there's something wrong with the GZK limit. Subsequent surveys have found other ultra-high energy cosmic rays, some approaching the oh my god particle's energy. The Auger Observatory has been studying them. The mysterious thing is that they don't clearly point back to known sources, the powerful objects that might be able to accelerate particles to these energies, like active galactic nuclei or gamma-ray bursts. Something out there is firing subatomic bullets at us with the energy of thrown baseballs. We don't know what it is. Story 8: The Fermi Bubbles. Two enormous gamma-ray structures extend from the center of our galaxy, and we don't know what made them in 2010. Astronomers analyzing data from the Fermi Gamma-Ray Space Telescope noticed something extraordinary about our own galaxy that had been hidden in the data. Two enormous, roughly spherical lobes of gamma-ray emission extending above and below the center of the Milky Way, each about 25,000 light-years tall. Together, the Fermi bubbles are roughly as tall as the galaxy itself is wide. They're emitting gamma rays, extremely high-energy photons, suggesting enormous amounts of energetic particles, and they have a surprisingly sharp edge where the gamma-ray emission cuts off, rather than fading gradually. Sharp edges in astrophysics usually mean something dynamic happened, a shock wave, a sudden event, rather than slow diffusion. Two main explanations are being debated. The first, a past period of intense activity from Sagittarius A, the supermassive black hole at the center of the Milky Way. Sag A is currently quiet, but if it had a major feeding event a few million years ago, consuming significant amounts of gas, the energy output could have driven these bubbles outward. The second, a burst of intense star formation in the galactic center, with the collective winds and supernova explosions from a large population of stars driving the outflow. Both explanations can produce bubbles. Neither one has been definitively confirmed as the cause. The energy stored in the Fermi bubbles is enormous, roughly equivalent to 1 million supernova explosions, and something put it there, probably a few million years ago, and whatever happened changed the environment around our entire galaxy. We live in a galaxy that had something dramatic happen at its center not that long ago, astronomically speaking. We're still figuring out what. Story 9, Big Bang nucleosynthesis, is one of the success stories of cosmology. The theory of how the very early universe, in the first few minutes after the Big Bang, produced the lightest elements, hydrogen, helium, and trace amounts of lithium, makes specific, testable predictions about how much of each element should exist. For hydrogen and helium, the predictions match observations beautifully. For lithium-7, they don't. The prediction, old stars, population 2 stars, formed from the primordial gas of the early universe with minimal contamination from later nucleosynthesis, should contain a specific amount of lithium-7. The observation, these old stars consistently contain about 3 times less lithium-7 than predicted. This is called the cosmological lithium problem, and it's been unresolved since the 1980s. The possibilities are frustrating because none of them are clean. Option 1. The Big Bang nucleosynthesis prediction is wrong. There's some physics in the early universe we don't understand that reduce lithium-7 production. Option 2. The old stars are destroying their lithium-7 internally through nuclear reactions, and we're seeing a depleted value rather than the primordial one. Option 3. Some measurement is systematically wrong. Option 2. Stellar depletion is currently the most discussed, but it requires old stars to deplete lithium at specific rates that are difficult to reconcile with what we know about stellar physics. The stars that show the lithium plateau, the consistent, apparently primordial lithium abundance, are diverse enough in their properties that uniform depletion seems unlikely. The universe made lithium-7 in a specific quantity 13.8 billion years ago. We can't find where it went. The problem is 40 years old and still open. Story 10, when the James Webb Space Telescope started returning its first deep-field images, the scientific community's reaction contained an element of alarm alongside the wonder. JWST was finding galaxies from the early universe, just a few 100 million years after the Big Bang, that appeared to be far more massive, far more structured, and far more chemically mature than the models of galaxy formation said should be possible. The standard model of galaxy formation says that the first galaxies should be small, irregular, and made almost entirely of hydrogen and helium, the only elements available from Big Bang nucleosynthesis. They should be building up stellar mass slowly over time as gravity pulls gas together and star formation proceeds. You shouldn't find large, mature, chemically enriched galaxies very early in cosmic history because there hasn't been enough time for all that to happen. JWST found galaxies from the first 500–700 million years of the universe's existence that look like they shouldn't be possible yet. Some appear to have stellar masses comparable to the Milky Way today, at a time when the Milky Way itself didn't exist. Some show signs of chemical enrichment, elements heavier than hydrogen and helium, that suggest multiple generations of stars have already lived and died. The response from cosmologists has been, either our galaxy formation models are significantly wrong in ways we need to understand, or these galaxies' masses and ages are being systematically overestimated due to some observational bias, or both. The debate is ongoing. JWST's early observations have genuinely challenged parts of the standard model of how galaxies form, and the field is working through what that means. The universe apparently made large galaxies faster than we thought was possible. We're still figuring out how. Story 11, Odd Radio Circles Redux. The universe keeps surprising us with giant things we don't have explanations for. Let's sit with ORCs for a moment longer, because the specific quality of the surprise they represent is worth unpacking. We've been doing radio astronomy since the 1930s. We've mapped the radio sky extensively. We have sky surveys that cover most of the observable sky. And yet, a category of enormous cosmic structure, hundreds of thousands to millions of light years across, went completely undetected until 2020. How? The answer is sensitivity and resolution. The Australian SCA Pathfinder telescope is a new generation of radio telescope capable of detecting much fainter radio emission over wide fields than was previously possible. The ORCs were always there, we just didn't have equipment sensitive enough to find them until now. Which raises an uncomfortable question. What else is there? What other categories of large-scale cosmic structure are sitting in the universe right now, detectable in principle, just waiting for us to build an instrument capable of finding them? The universe has consistently surprised us when we open new observational windows. Infrared, X-ray, gamma ray, gravitational waves, and now the high-sensitivity radio surveys that found ORCs. For ORCs specifically, the current best model, concentric shock waves from some kind of energetic event at a central galaxy, is plausible but unproven. The ORC-forming event would need to be extraordinarily energetic, and the structure would need to survive for potentially billions of years as it expanded. We've found about half a dozen confirmed ORCs. Statistical analysis of their properties requires more examples than we have. New generations of telescopes, the Square Kilometre Array being built now, will find more. The hope is that with enough examples, the pattern that explains them will become clear. Right now, they're a new type of thing in the universe, with no confirmed explanation. Story 12, Hoag's Object. A perfectly symmetric ring galaxy that has no satisfying explanation for why it looks like that. In 1950, astronomer Arthur Hoag discovered an object in the constellation Serpens that he initially thought might be a planetary nebula, a dying star surrounded by a shell of gas. It wasn't. It was a galaxy. Specifically, it was one of the strangest galaxies ever photographed, a compact, old, yellow nucleus surrounded by a gap of nearly empty space, surrounded by a ring of young, hot blue stars, with the whole thing being essentially perfectly circular and symmetric. Hoag's object is classified as a ring galaxy, but it's an extreme example. Ring galaxies typically form through collisions. A smaller galaxy punches through the disk of a larger one, sending a shockwave outward that triggers a ring of star formation. Hoag's object doesn't show obvious signs of a recent collision. The nucleus looks old and undisturbed. There's no obvious culprit galaxy nearby. There's also a detail that's genuinely eerie. In the gap between the nucleus and the outer ring, you can see another ring galaxy in the background through the gap, just visible. The probability of that alignment is vanishingly small. It means nothing scientifically, but it's the kind of detail that makes a photograph look staged. The explanations proposed for Hoag's object: a very old collision whose evidence has faded, self-propagating star formation driven by the nucleus in some poorly understood way, a gravitational interaction with another object that's since moved away, a freak of orbital mechanics that produced a stable ring configuration. Hoag's object is so symmetric and so isolated that it's hard to fit into standard galaxy formation scenarios. It looks like someone drew it with a compass. How it got that way and how it stays that way is still debated among galaxy formation specialists. Story 13, the Galactic Center GV excess. There's more gamma radiation at the heart of the Milky Way than there should be. When astronomers analyzed years of data from the Fermi Gamma Ray Space Telescope focused on the center of our galaxy, They found more gamma-ray emission than known sources could account for. The excess peaks at a few GeV in energy, the GeV excess, and it has a very specific spatial distribution, roughly spherically symmetric around the galactic center. The reason this is exciting, and the reason it's been generating substantial scientific interest since it was identified around 2009-2010, is that this is exactly what you'd expect if dark matter particles in the galactic halo were annihilating each other. Dark matter particles are predicted by some models to annihilate when they collide, producing gamma rays of specific energies. The galactic center is where dark matter density would be highest. The energy spectrum and spatial distribution of the GeV excess are consistent with certain dark matter annihilation models. That's the exciting possibility. The boring but plausible alternative: an unresolved population of millisecond pulsars in the galactic bulge. Millisecond pulsars are old, rapidly spinning neutron stars that also produce gamma rays, and we know they exist in large numbers in the galactic bulge. If there are more of them than we've cataloged individually, their combined emission could account for the excess without any new physics. This is genuinely difficult to resolve because millisecond pulsars in the galactic bulge are too faint and too numerous to resolve individually with current instruments. We'd need a significant improvement in gamma-ray telescope resolution to distinguish individual pulsars. Either the center of our galaxy is crackling with dark matter annihilation, or it's packed with old spinning dead stars. Both are real possibilities. Neither is confirmed. Story 14: the Hercules Corona Borealis Great Wall, a structure so large that standard cosmology says it shouldn't exist. One of the fundamental assumptions of standard cosmology is the cosmological principle that the universe, on large enough scales, is roughly uniform. It looks the same in every direction, with matter distributed homogeneously when you zoom out far enough. This isn't just an aesthetic preference. It's baked into the mathematical framework of our cosmological models. Without it, the equations become intractable. The Hercules Corona Borealis Great Wall was identified in 2013-2014 through observations of gamma-ray bursts, explosions so bright they can be seen billions of light years away, used as tracers of the underlying distribution of galaxies. The structure is an overdensity of gamma-ray bursts, and by implication, of galaxies, spanning approximately 10 billion light-years in its longest dimension. To put that in context, the observable universe is about 93 billion light-years across. The Hercules Corona Borealis Great Wall is about 10% of the observable universe in size. Standard cosmological models say that structures larger than about 1.2 billion light-years shouldn't exist. The universe hasn't had time to gravitationally assemble anything bigger. And the homogeneity assumption says there shouldn't be enough matter over density to do it anyway. The structure challenges the cosmological principle in a direct way. If it's real and as large as it appears, there's something wrong with our understanding of how matter is distributed in the universe at the largest scales. The caveats: the identification relies on gamma-ray burst statistics, which have significant uncertainties. Some astronomers argue the structure is a statistical artifact rather than a true coherent structure. The debate about whether the Hercules Corona Borealis Great Wall is real, and if so what it means, is ongoing. If it's real, it's too big to exist under our best models. If it's not real, we still need to explain the gamma-ray burst distribution that produced the apparent signal. Story 15: the Sun's corona heating problem. The outer atmosphere of our star is mysteriously millions of degrees hotter than its surface. The surface of the Sun, the photosphere, is approximately 5,500 degrees Celsius. As you move away from the surface into the corona, the Sun's outer atmosphere, the temperature rises dramatically, counterintuitively, to somewhere between 1 and 3 million degrees Celsius. The corona is hundreds of times hotter than the surface below it. This breaks basic thermodynamics intuition. Heat should flow from hot regions to cold ones. Moving away from the heat source, the surface, should make things cooler, not hotter. If you hold your hand near a fire, it gets warmer the closer you are, not cooler. The corona heating problem has been known since the 1940s and has been one of the major open questions in solar physics for over 80 years. The energy to heat the corona clearly comes from the sun. There's no other source nearby. But the mechanism by which energy is transported from the surface up through the corona with such efficiency as to produce million-degree plasma is not established. Two leading mechanisms are proposed: wave heating. Alphean waves, oscillations in the magnetic field, propagate upward from the solar surface and dissipate their energy in the corona. Nanoflare heating, countless tiny magnetic reconnection events in the corona, each releasing a small burst of energy, with the cumulative effect providing the observed heating. Both mechanisms are physically plausible, and both are supported by some observational evidence. The Parker Solar Probe, launched in 2018, has been flying closer to the sun than any previous spacecraft and has directly sampled the solar corona. Its observations are providing new data relevant to this question. The mystery is 80 years old. The probe flying through the corona may finally provide the answer. Story 16: Fast radio bursts. Millisecond radio pulses from the deep universe that are still being figured out. Fast radio bursts, FRBs, are millisecond duration pulses of intense radio emission from cosmological distances. The first one was discovered in 2007 in archival data from 2001, and since then, hundreds have been detected. They're incredibly bright, some releasing more energy in a millisecond than the sun does in thousands of years, and they come from billions of light years away. The basic picture has become clearer. In 2020, a magnetar in our own galaxy produced an FRB-like burst, which was a major breakthrough linking these ultra-magnetic neutron stars to at least some FRBs. Magnetars, the remnants of certain supernovae with the strongest magnetic fields known in the universe, are now a leading explanation. But magnetars don't explain everything. Most FRBs are one-off events. Some repeat. A handful repeat in regular patterns. FARB 180916 repeats with a 157-day cycle. Magnetar flares don't obviously produce regular periodicity on this timescale. The galactic magnetar burst was roughly 1,000 times less energetic than the most powerful extragalactic FRBs. There may be multiple types of FRB with different origins. The repeating FRBs are the specifically puzzling ones. 157 days is a very specific period. Proposed explanations: the orbit of the magnetar around a companion star, with the cycle reflecting when the burst can escape through the companion's wind. Precession of the magnetar, some kind of orbital or geometric effect that creates activity windows. None of these has been confirmed. FRBs went from "what is that?" in 2007 to partly understood but with multiple remaining mysteries in 2024. The rate of discovery is increasing as more sensitive surveys come online. Every new FRB population they find seems to add new complexity to the picture. Story 17: Population 3 stars. The first stars in the universe have never been directly observed when the universe was about 400 million years old. During a period called the Cosmic Dawn, the first stars switched on. These are called Population 3 stars, and they would have been extraordinarily different from modern stars, made entirely of hydrogen and helium, the only elements available from Big Bang nucleosynthesis, with no heavier elements at all. They would have been impossibly massive by modern standards. Theoretical models suggest they may have been hundreds to thousands of times more massive than the Sun, living for only a few million years before dying in spectacular explosions that seeded the universe with the first heavy elements. We've never directly observed a population 3 star. They should all be dead. Their short lifespans and great distance in both space and time place them at the edge of observability. To see them requires looking so far away that you're looking at light from 13+ billion years ago, which means seeing them as they appeared when the universe was a few % of its current age. The James Webb Space Telescope was specifically designed partly to probe the era of cosmic dawn, and it's showing us some of the earliest galaxies ever seen. Whether it can detect individual population 3 stars or their collective signatures is one of the things astronomers are actively looking for in JWST data. There may be traces of population to 3 stars in extremely metal-poor stars in our own galaxy, stars that formed from gas that was only slightly contaminated by the first stellar explosions. The elemental abundances in these ancient stars might carry signatures of population to 3 chemistry. The first generation of stars in the universe changed everything that came after them. We've never seen one. Story 18, the muon anomaly, a precisely measured property of muons, doesn't match the Standard Model's prediction. The muon G2 experiment at Fermilab is measuring a property of muons, the heavier cousins of electrons, called the anomalous magnetic moment, often written as G2. This is a quantity that the Standard Model of particle physics can calculate with extraordinary precision, and that can be measured experimentally with extraordinary precision. The point of the experiment is to compare the two and see if they match. They don't quite match. The measured value of muon G2 is slightly larger than the Standard Model prediction. The discrepancy is small in absolute terms but statistically significant, at the level of about 4-5 sigma. This is below the 5 sigma threshold conventionally required for a discovery in physics, but it's substantial enough to take seriously. If the discrepancy is real, if it's not caused by a systematic error in the measurement or in the theoretical calculation, it means there are particles or forces interacting with the muon that the Standard Model doesn't include. New physics, a fifth force, a new particle, something outside the current framework. The complication: in 2021, a lattice QCD calculation was published that gave a slightly different theoretical prediction, one that was closer to the measured value, reducing the tension. Whether the lattice QCD calculation or the older theoretical approach is more correct is now itself a significant debate in the particle physics community. So, a measurement that disagrees with the Standard Model, an alternative calculation that partially resolves the disagreement, and physicists arguing about which calculation to trust, whether muon G2 is pointing toward new physics or toward a theoretical refinement that cleans everything up, is still being worked out. Story 19, Planet 9. Something might be pulling on the outer solar system from a distance we've never looked at. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper arguing that the strange orbital clustering of a group of distant trans-Neptunian objects, icy bodies in the far outer solar system, was best explained by the gravitational influence of an undiscovered large planet. They called it Planet 9. The hypothetical planet would be roughly 5-10 times Earth's mass, orbiting at roughly 400-800 times Earth's distance from the Sun, taking between 10,000 and 20,000 years to complete one orbit. The specific gravitational signature that would cause the observed clustering requires something massive, distant, and on a specific inclined, eccentric orbit. A random distribution of trans-Neptunian objects wouldn't produce this alignment. The statistical argument for Planet 9, that the clustering is too coherent to be chance, has been a genuine debate in the field. The counter-argument: we've discovered most of these distant objects through surveys that have specific biases. The surveys look at certain parts of the sky more than others. The clustering might be an artifact of where we've looked, rather than evidence of a real planet. Statistical analyses of this potential bias have gone back and forth, with different teams reaching different conclusions. If Planet 9 exists, it should be findable by next-generation surveys, particularly the legacy survey of space and time that will be run by the Vera C. Rubin Observatory starting in 2024-2025. This survey will cover the southern sky repeatedly and deeply, and should either find Planet 9 or significantly constrain where it could be. It might be there. It might be a statistical artifact. A survey starting now may settle this within a few years. Story 20, the black hole mass gap. Gravitational wave detectors are finding black holes that shouldn't be able to form when a massive star dies. Depending on its mass, it leaves behind either a neutron star or a black hole. Stellar evolution theory predicts a specific range of black hole masses that can form from normal stellar collapse. roughly 5 to about 40-50 solar masses. Above that range, the physics of stellar death gets complicated in a way that produces what's called a mass gap, a range of masses between roughly 50 and 130 solar masses where normal stellar collapse shouldn't produce black holes, because stars in the right mass range undergo a different kind of collapse that doesn't leave a compact remnant. Then LIGO and Virgo started detecting gravitational waves from merging black holes and found some of them sitting squarely in the mass gap. GW 190521, detected in 2020, involved black holes of approximately 66 and 85 solar masses, both in the theoretically forbidden zone. The final merged black hole had a mass of about 142 solar masses, making it the first intermediate mass black hole detected by gravitational waves. How do you get black holes in the mass gap? Several options. They might form from the mergers of smaller black holes, two gap-sized black holes forming from smaller parents that merged. They might form in dense stellar environments where the physics of collapse is different. There might be something wrong with the pair instability models. There might be exotic formation channels we haven't properly considered. The mass gap black holes are real. They're radiating gravitational waves that detectors have measured. The mechanism that makes them is genuinely debated. The standard story of how massive stars die apparently has chapters we haven't written yet. Story 21, the gravitational wave background hum. Space itself is vibrating at ultra-low frequencies, and we don't know the source in June 2023. Multiple pulsar timing array experiments around the world. Groups of researchers who use arrays of millisecond pulsars as a cosmic gravitational wave detector simultaneously announced they had detected a gravitational wave background signal. Not a single gravitational wave event from a merger. A background hum. A pervasive, ultra-low frequency vibration of space-time itself, present everywhere in the universe. Gravitational wave backgrounds are predicted to exist. The question is where this one comes from. The most expected source. Countless pairs of supermassive black holes in the centers of merging galaxies throughout cosmic history. Each pair gradually inspiraling and emitting low-frequency gravitational waves. Add up billions of these over cosmic time, and you get a background hum. But the detected signal doesn't perfectly match the expected spectral shape from supermassive black hole binaries. It could still be black holes. The measurements need refinement, and the models have uncertainties. But the mismatch has opened up alternative possibilities. Some of those alternatives are genuinely exotic. Phase transitions in the very early universe, cosmic strings, or even signals from the inflationary period of the universe's birth. These would be extraordinary discoveries, carrying information about processes from the first fraction of a second after the Big Bang. The 2023 detections represent the first definitive observation of the gravitational wave background. Understanding what's generating it is now one of the central questions in gravitational wave astronomy. The signal is there. The source is still being determined. Story 22, the positron excess. More antimatter electrons are hitting Earth than any known source should be producing the Alpha Magnetic Spectrometer on the International Space Station, AMS-02, has been measuring cosmic ray particles since 2011 with extraordinary precision. Among its findings, a surprising excess of high-energy positrons, the antimatter counterpart of electrons, arriving at Earth from space. More positrons than standard models of cosmic ray production predict should be arriving. Positrons are produced naturally in various astrophysical processes, but the excess, particularly at energies above a few hundred GeV, is larger than can be easily accounted for by known sources. Something is producing a lot of high-energy positrons somewhere in the galaxy. The two leading explanations are at very different scales of excitement. The boring but plausible explanation: pulsars. Nearby millisecond pulsars are known to produce pairs of electrons and positrons, and a population of nearby pulsars could be responsible for the excess. Observations with other instruments have identified some potential pulsar candidates. The exciting explanation? Dark matter. If dark matter particles are WIMPs, weakly interacting massive particles. They can annihilate when they meet each other, and some annihilation channels produce electron-positron pairs. The galactic halo is full of dark matter, and if WIMP annihilation is happening at the right rate, it could produce the observed positron excess. AMS-02 is still collecting data, and its measurements are becoming more precise. The spectral shape of the positron excess, how the number of positrons changes with energy, is a key discriminator between the pulsar and dark matter explanations. So far, the data is consistent with both. More precision is needed, and AMS-02 is providing it, slowly. Story 23, ultraluminous X-ray sources. Too bright for normal black holes, too small for giant ones. They might be a missing category. Black holes come in two well-established categories. Stellar mass black holes, formed from the collapse of individual massive stars, range from a few to a few tens of solar masses. Supermassive black holes, residing in the centers of most large galaxies, range from millions to billions of solar masses. These two categories are well observed and understood. What about the gap in between? Intermediate mass black holes, hundreds to thousands of solar masses, are theoretically expected but extremely difficult to confirm observationally. And then, there are ultraluminous X-ray sources, or ULXs. ULXs are X-ray sources in other galaxies that are too bright to be explained by a normal stellar mass black hole accreting matter at the maximum rate allowed by physics. But they're not in the centers of galaxies where supermassive black holes live. For years, the most natural explanation was intermediate mass black holes. A black hole of a few thousand solar masses would naturally produce the observed X-ray luminosity. Then astronomers found pulsations, regular, rapid pulses, in some ULXs, which proved they couldn't be black holes at all. Pulsations are a signature of neutron stars, and these neutron stars were accreting matter at rates far beyond what physics says should be possible, somehow producing luminosities normally associated with black holes. Neutron stars that radiate far more than the Eddington limit, called ultraluminous X-ray pulsars, are now a confirmed exotic class of objects. So ULXs contain both neutron stars breaking luminosity limits and possibly intermediate mass black holes. Understanding which ULXs are which and how neutron stars can radiate so much is an ongoing and genuinely exciting puzzle. Story 24 AT 2018 Cow. The Cow, a cosmic explosion brightened and faded in days and nobody agrees what it was. In June 2018, a telescope in Hawaii detected a transient astronomical event that was immediately strange. It brightened to peak luminosity in just 3-4 days. Normal supernovae take weeks, and then faded rapidly, all while being exceptionally blue and hot. Its astronomical designation was AT 2018 Cow. Everyone called it the Cow. The Cow was approximately 200 million light-years away and was about 100 times more luminous than a typical supernova at peak. It had an extremely hot temperature, tens of thousands of Kelvin, and its emission was detected across a huge range of the electromagnetic spectrum, from radio waves to X-rays. What is it? The debate has been ongoing. Leading candidates: a failed supernova directly forming a black hole. The stellar core collapses directly to a black hole without exploding normally, and the energy we see comes from the shock of the collapse. This would make the Cow one of the first direct observations of a stellar mass black hole's birth. A compact object embedded in dense material, a neutron star or black hole formed in a supernova and then rapidly accreted a huge amount of material from a surrounding envelope, producing the unusual brightness and fast evolution. A tidal disruption event, a star being torn apart by an existing black hole, though the location didn't match what you'd expect for a galactic nucleus hosting a supermassive black hole. Follow-up observations found evidence for a central X-ray source consistent with a compact object, potentially a neutron star or new black hole, embedded in the ejecta, but none of the explanations has been fully confirmed. The Cow has now spawned a whole new class of luminous fast blue optical transients, similar events being found in surveys. Each new example adds to the puzzle rather than resolving it. Story 25. Dark matter is supposed to be the scaffolding of the universe. The standard model of structure formation says that dark matter halos formed first, and then ordinary matter fell into them to form galaxies. Dark matter should be everywhere there are galaxies, and galaxies without significant dark matter halos shouldn't really exist. In 2018, Peter Van Dockum and colleagues published observations of a galaxy called NGC 1052 DF2 that appeared to have little to no dark matter. The galaxy's globular clusters, used as tracers of the gravitational potential, were moving far too slowly for the dark matter content a galaxy of its size should have. It seemed almost entirely made of ordinary matter. A second such galaxy, NGC 1052 DF4, was found nearby, similarly dark matter deficient. And then it got stranger. DF4 appeared to be in the process of being tidally disrupted, torn apart by the gravity of a nearby larger galaxy, suggesting its dark matter, whatever little it had, may have already been stripped away. This discovery was initially celebrated by advocates of alternative gravity theories, modified Newtonian dynamics, and similar frameworks, because a galaxy without dark matter would seem to disprove the need for dark matter as a fundamental component. But it actually complicated the alternative gravity picture. MON doesn't naturally produce galaxies without dark matter either, and explaining why these specific galaxies lack dark matter is difficult under any framework. The current best explanation under dark matter theory, tidal interactions stripped the dark matter from these galaxies, or prevented them from acquiring normal dark matter halos. This is possible, but requires specific circumstances. Galaxies without dark matter shouldn't exist, but they do. Explaining them is hard for everyone. Story 26. Rogue planets. There may be more free-floating planets than planets orbiting stars. Most planets in our solar system, and in the planetary systems we detect around other stars, orbit a host star. This seems obvious. Planets form in protoplanetary disks around young stars, after all. Where else would they be? Anywhere, as it turns out. Gravitational interactions in young planetary systems can eject planets entirely, flinging them out of their solar system into interstellar space. These rogue planets, free-floating planets with no host star, drifting alone through the galaxy, should exist in principle. Recent observations suggest they may exist in astonishing numbers. Microlensing surveys, which detect the gravitational lensing effect of foreground objects passing in front of background stars, have detected dozens of candidate rogue planets. Statistical analysis of these detections suggests that rogue planets may outnumber stars in the galaxy. Some estimates suggest there could be trillions of Earth-mass rogue planets, plus a significant population of larger free-floating bodies. If there are more rogue planets than planets orbiting stars, something about current planet formation models needs adjustment. Either the ejection rate during planetary system formation is higher than expected, or there are formation channels, planets forming in space from collapsing gas without a stellar nursery that we haven't fully accounted for. JWST has been finding candidate rogue planets, objects dubbed Jupiter mass binary objects, even in pairs, which is particularly strange. Free-floating planetary mass objects forming in binaries challenges the standard formation picture. Something is producing a lot of planets without stars. What and how is still being worked out. Story 27. The missing antimatter problem. Everything you can see in the universe shouldn't be here. The Big Bang should have produced equal amounts of matter and antimatter. That's what the equations of particle physics say. The fundamental processes that create particles create them in matter-antimatter pairs, symmetrically. If the universe began in the high-energy state of the Big Bang, matter and antimatter should have been created in equal quantities. Equal amounts of matter and antimatter annihilate when they meet, producing pure energy. If the Big Bang made equal quantities, the universe should have annihilated itself into a bath of photons almost immediately, with nothing left over to make stars, galaxies, planets, or us. Something broke the symmetry. Matter won. By how much? by roughly 1 part in a billion. For every billion matter-antimatter pairs that annihilated, there was one leftover matter particle. That 1 in a billion excess is everything you can see in the universe, every atom of every galaxy. The physics term for the mechanism that broke the symmetry is baryogenesis. We don't know what it was. The standard model of particle physics contains CP violation, a small asymmetry between matter and antimatter in certain particle interactions, but the amount of CP violation in the standard model is vastly insufficient to produce the observed matter-antimatter asymmetry. There must be additional CP violation from unknown physics that tipped the balance at the beginning. Finding where baryogenesis came from is one of the deepest questions in particle physics and cosmology. Experiments like those at the T2K neutrino experiment are looking for CP violation in neutrinos, which might be part of the answer. But the mechanism that produced you and everything you can see is not yet understood. Story 28, the cosmic ray knee. There's an unexplained kink in the energy distribution of particles hitting Earth from space. Cosmic rays, high-energy particles arriving at Earth from space, span an enormous range of energies, from relatively modest to the extreme energies of the oh my god particle. When you plot how many cosmic rays arrive at each energy level, you get a smooth curve that falls off as energy increases. More low-energy cosmic rays, fewer high-energy ones. Except at a specific energy, around 1015.5 electron volts, or about 31015 eV, the slope of that curve changes. It becomes steeper. Fewer high-energy cosmic rays above this point than a smooth extrapolation would predict. This kink in the spectrum is called the knee. It's been observed since the 1950s. It's been confirmed by many independent experiments with different detection techniques. It's real. What causes it? The leading theories: above the knee energy, cosmic rays can escape our galaxy more easily, so the observed spectrum reflects a combination of galactic sources and energy-dependent escape rates, or the sources that produce cosmic rays up to the knee energy, probably supernovae in our galaxy, can accelerate particles beyond that energy. And higher energy cosmic rays come from different, more powerful sources. Or there's a transition between different types of sources at the knee energy. Different pieces of evidence point toward different explanations, and the composition of cosmic rays near the knee, whether they're mostly protons or heavier nuclei, has been measured with inconsistent results by different experiments, which matters for distinguishing between models. The knee has been in the data for 70 years. A clean single-source explanation has not emerged. Story 29, magnetar glitches. The most magnetically extreme objects in the universe occasionally change their spin rate for unexplained reasons. Pulsars, rapidly spinning neutron stars that beam radio waves like cosmic lighthouses, are among the most precise natural clocks in the universe. Their spin rates are extraordinarily stable, slowing down only very gradually as they lose energy. This stability is one of the things that makes pulsar timing so useful for precision measurements. Occasionally, pulsars glitch. Their spin rate suddenly increases, a spin up, and then slowly relaxes back toward the normal spin-down trend over weeks to months. Magnetars, neutron stars with extraordinarily powerful magnetic fields, up to 10-15 Gauss compared to Earth's 0.5 Gauss, glitch too, sometimes dramatically. The physics of pulsar glitches is not fully understood. The leading model involves the neutron star's interior, a superfluid layer of neutrons that has been spinning faster than the solid crust, accumulating angular momentum, and then suddenly coupling to the crust and transferring that momentum, causing the observed spin up. This is consistent with some observations and not with others. For magnetars, the situation is more complicated because their behavior is dominated by their extreme magnetic fields in ways that standard neutron star physics doesn't fully describe. Magnetar glitches are often accompanied by bursts of X-rays and sometimes by FIRB, like radio emission, connecting to the FRUB mystery. The specific timing and magnitude of magnetar glitches, when they happen and why, cannot be predicted with current models. Something changes suddenly in an object as extreme as a city-sized ball of nuclear density matter with a magnetic field of 1,000,000 suns, and we don't fully understand the internal physics that drives it. Story 30: The impossible early supermassive black holes. Black holes that are too big for how young the universe was when they formed in the first billion years of the universe's existence. Black holes had a problem. They hadn't had enough time to grow very big. A black hole grows by accreting matter, pulling in gas and other material, and even accreting at the theoretical maximum rate. It takes a long time to grow from a stellar mass black hole to a supermassive one containing billions of solar masses. And yet astronomers have found supermassive black holes, quasars powered by actively accreting black holes, at redshifts corresponding to when the universe was less than 1 billion years old. Quasars are extremely luminous because the black holes powering them are so massive and accreting so much material. Finding them at very high redshift means they existed when the universe was very young, and that means these black holes grew to billions of solar masses extraordinarily quickly. Under standard accretion physics, this doesn't work. You can't grow a billion solar mass black hole in under 1 billion years, starting from a stellar mass seed, without either violating the Eddington limit significantly or starting from a much larger seed than normal stellar collapse provides. Proposed solutions: super Eddington accretion. Somehow accreting material much faster than the standard limit allows. Direct collapse black holes. Massive gas clouds in the early universe collapsing directly into large black holes without going through the star stage. Or mergers of many smaller black holes building up mass faster than single accretion events. JWST is now finding even more early massive black holes, making the problem potentially worse than it appeared before the telescope launched. How the universe grew black holes so fast at the beginning is genuinely not solved. Story 31: The Edge's 21 cm signal. The early universe's hydrogen was somehow much colder than it should have been in 2018. The Edge's experiment in Western Australia reported a detection of a radio absorption signal from neutral hydrogen in the early universe, specifically from an era around 180 million years after the Big Bang, when the universe was transitioning from a fog of neutral hydrogen to ionized plasma as the first stars lit up. The signal was there, a detection of the 21 centimeter hydrogen absorption line from the early universe, which was a genuine first and a significant achievement. The problem was its depth. The absorption feature was roughly twice as deep as the most optimistic models predicted it should be. A deeper absorption feature means the hydrogen gas in the early universe was colder than expected relative to the surrounding radiation. How do you make primordial gas colder? One radical possibility: interactions between hydrogen and dark matter. If dark matter particles were exchanging energy with the hydrogen gas in the early universe, they could have cooled the gas below the expected temperature, producing the deeper than expected absorption. This would be remarkable, an indirect detection of dark matter through its effect on the temperature of early universe hydrogen. The Edge's signal was published in Nature and immediately generated enormous attention, and then other experiments tried to confirm it and found ambiguous results. The 21 cm cosmology field is difficult. Terrestrial radio frequency interference is a significant challenge, and whether the Edge's signal is real or an instrumental artifact is still debated. If it's real, it might be telling us something about dark matter's properties. If it's not real, it's a cautionary tale about signal detection in radio astronomy. Story 32: PSRB 157 plus 12's pulsar planets. The first confirmed exoplanets orbit a dead, irradiating star, and we don't know how the first confirmed exoplanets, planets orbiting another star, were not found around a normal sun-like star. They were found in 1992 orbiting a pulsar. SAR-B 157 plus 12 is a millisecond pulsar, a rapidly spinning neutron star that is the collapsed remnant of a dead massive star, and it has at least 3 confirmed planets orbiting it. This is strange for multiple reasons. A pulsar is an extraordinarily hostile environment. The neutron star blasts its surroundings with intense radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Any planet orbiting a pulsar would be bathed in radiation levels that would strip away atmospheres and bombard any surface with energetic particles. The environment is about as hostile to life as it's possible for an astrophysical environment to be. How do these planets exist? Two main hypotheses. They're remnants of the original stellar system that survived the supernova explosion that created the pulsar. Though surviving a supernova is extraordinarily difficult, and the planets would need to have reformed from the debris, or they formed after the supernova from material ejected in the explosion that remained in orbit and gradually coalesced into planets around the pulsar remnant. The second hypothesis, post-supernova planetary formation, is currently considered more likely, but the specific details of how a disk of stellar debris around a pulsar forms planets on the timescale we observe is still not fully worked out. It would require relatively rapid planet formation in a very unusual chemical and radiation environment. The first planets we ever confirmed outside our solar system orbit a dead star. Their existence is still not fully explained. Story 33 long gamma ray bursts without supernovae. Some stellar collapse events are missing their expected explosion. Gamma ray bursts are the most energetic explosions in the universe. They come in two broad categories. Short GRBs, lasting less than about 2 seconds, are now well understood to come from the merger of two neutron stars, confirmed by the gravitational wave detection of GW170817 and its associated short GRB. Long GRBs, lasting more than 2 seconds, are associated with the collapse of massive stars, a specific type of stellar death called a collapsar that produces a jet of material moving near light speed, and the jet produces the gamma ray burst. Long GRBs should be accompanied by supernovae. When a massive star collapses, the outer layers rebound and explode as a supernova, a dramatic stellar explosion bright enough to briefly outshine an entire galaxy. Follow-up observations of nearby long GRBs typically find a supernova brightening in the weeks after the burst as the supernova ejecta expands and cools. Some don't. A handful of well-studied long GRBs have been followed up with careful observations, and no supernova has appeared, despite the sensitivity being high enough to detect a supernova if it were there. What happens instead of a supernova? The leading explanation: direct collapse. The stellar core collapses directly to a black hole without the rebound that produces a supernova. If the collapse is complete and direct, the material all falls inward and nothing is ejected outward. The gamma ray burst is produced by the jet, but there's no supernova envelope to expand and brighten. This would make these GRBs signposts for direct-to-black hole stellar collapse, one of the proposed mechanisms for the impossible early supermassive black holes. But observationally confirming that no supernova happened is difficult. Absence of evidence is always tricky. Story 34, the Great Repeller. A vast cosmic void is pushing our galaxy away from it. Our galaxy is moving. Not just expanding with the universe, moving relative to the average expansion, pulled and pushed by the gravitational influences of the surrounding large-scale structure. The Great Attractor, a concentration of mass toward the constellation Centaurus, has been known for decades to be pulling our galaxy and others in its direction. In 2017, astronomers mapped the large-scale structure around us and identified something they called the Dipole Repeller, now sometimes called the Great Repeller, a vast underdense region, a supervoid, in the direction roughly opposite the Great Attractor, toward the constellations Leo and Gemini. While the Great Attractor pulls our galaxy toward Centaurus, the Great Repeller pushes us away from itself, and both effects work in the same direction, explaining our overall motion through space. This is conceptually important. It was previously assumed our motion was dominated by attraction toward dense regions. The identification of the repelling void shows that pushing from underdense regions contributes comparably. Voids push because they contain less gravity than average. Matter around the void falls away from it rather than toward it. And galaxies adjacent to the void get pushed away. The Great Repeller's specific extent, mass deficit, and contribution to our motion are still being characterized. The 2020 discovery of the South Pole Wall, an enormous structure on the other side of the sky, has added additional complexity to the picture of what's shaping our galaxy's motion through the large-scale cosmic web. We live in a universe of gravitational tug-of-war, and we're still mapping the hands that are pulling and pushing. Story 35: Quasar Spin Alignment. Distant quasars are spinning in the same direction across billions of light-years. Quasars are among the most distant and luminous objects in the universe, active galactic nuclei powered by supermassive black holes accreting material at enormous rates. Their jets, beams of material ejected from the black hole's poles, point in directions related to the black hole's spin axis. In 2014, and in subsequent studies, astronomers found something that genuinely shouldn't be possible under standard cosmology. The spin axes of distant quasars across huge stretches of space appear to be non-randomly aligned with each other. Quasars that are billions of light-years apart in the same large-scale filaments of the cosmic web tend to have their spin axes pointing in similar directions. This is unexpected because the cosmological principle says the universe should be statistically uniform, there's no preferred direction, and there shouldn't be any correlation in the orientations of objects across such enormous distances. The physics of black hole formation and spin acquisition is local. It depends on what gas happens to be falling in from which direction. And there's no mechanism in standard cosmology for information about the preferred spin direction to propagate across billions of light years. The proposed explanation is large-scale structure, the cosmic web itself. The filaments and sheets along which galaxies and quasars are distributed might influence the spin axes of objects forming within it through tidal torquing. The same large-scale structure that determines where galaxies form might also influence their orientation and spin through gravitational tidal effects operating at cosmological scales. This is speculative. The alignment signal is real in multiple datasets, but its interpretation is debated. If confirmed, it suggests the large-scale structure of the universe influences objects at the scales of individual supermassive black holes, a connection across scales that standard models didn't fully anticipate. Story 36: The Magnetar-Ferb Connection. We know magnetars make some FRBs, but the most powerful ones still don't fit the 2020 detection of an FRB like burst from SGR 1935 plus 2154. A magnetar in our own galaxy was a breakthrough moment for fast radio burst research. For the first time, we had direct observational evidence linking magnetars, neutron stars with extreme magnetic fields, to FRB-like events. It seemed like the major mystery of FRBs might be close to resolution. The specific burst from SGR 1935 plus 2154 was orders of magnitude less powerful than the most energetic extragalactic FRBs, about 1,000 times weaker at the same distance. But extrapolation suggested that a similar event at extragalactic distances would look like a faint FRB. The picture seemed to fit. Except the most energetic FRBs don't fit the picture as cleanly. The energy budget of the most luminous FRBs is so large that producing them from standard magnetar flares requires either very nearby sources or magnetar activity significantly more extreme than we've ever observed in galactic magnetars. Some FRBs occur in environments such as near the centers of star-forming galaxies, that don't obviously match the expected environments of isolated neutron stars. The repeating FRBs are a separate puzzle. SGR 1935 plus 2154 has produced multiple bursts, but not with the regular 157-day periodicity of FARB 180916. Where does a 157-day period come from in any magnetar model? The current picture is that magnetars explain some FRBs, probably many of them. But the population of FRBs is diverse enough that magnetars might not explain all of them. There might be multiple types of FRB from multiple types of source. The mystery has been partially solved in a way that revealed its full complexity. Story 37, the Sombrero Galaxy's oversized bulge. This galaxy doesn't fit any standard category, and nobody agrees why galaxies come in shapes. Spiral galaxies have disks with spiral arms and a central bulge. Elliptical galaxies are smooth, rounded, and don't have disks. Lenticular galaxies are somewhere in between, disc-shaped but without spiral structure. These classifications work reasonably well for most galaxies. The Sombrero Galaxy doesn't fit. It has a disk, suggesting a spiral or lenticular galaxy. But its central bulge, the rounded component at the galaxy's heart, is enormous relative to the disk, far larger than any normal spiral galaxy has. The bulge contains about 90% of the total stellar mass. Normal spiral galaxies have bulges that are much smaller fractions of the total. At its center sits a supermassive black hole of approximately 1 billion solar masses, enormous even by galaxy center standards. The bulge's stellar population is old and red, like an elliptical galaxy, while the thin outer disk has star formation ongoing. Classification attempts have oscillated between calling it an edge on lenticular galaxy with an unusually prominent bulge, a spiral galaxy that somehow grew an enormous elliptical galaxy-like component, or a hybrid that doesn't fit standard categories. Formation scenarios proposed. The Sombrero may be the result of a major merger in which an elliptical galaxy merged with a disk galaxy, preserving the disk structure while adding enormous stellar mass to the bulge. Or it may have formed in an unusual environment that favored early, massive bulge growth while maintaining a thin disk. The Sombrero is one of the most photographed galaxies in the sky. How it got to look the way it does is still genuinely debated. Story 38, white dwarf flickering. Some dead stars are rapidly brightening and dimming in ways that don't match any known model white dwarfs. The dense remnants of dead stars like our sun can pulsate. Certain types of white dwarfs oscillate in brightness as pressure waves travel through their interiors, and these pulsations are well studied and well modeled. White dwarf astroseismology, using the pulsations to probe the star's interior structure, is a mature field. Some white dwarfs are flickering in ways that don't match the known pulsation models. Rapid, irregular brightness variations on timescales of minutes that don't have the regular periodicities of normal pulsations and that don't correspond to any well-understood stellar oscillation mode. The possible explanations range from internal to external. Internal, some new type of stellar oscillation mode in the white dwarf itself that current models don't predict. External, something orbiting the white dwarf, disrupted planetesimals, asteroids, or planetary debris, passing in front of the star and causing brief dimmings, or heating a spot on the stellar surface as it interacts. White dwarf systems are increasingly understood to be common sites of planetary system disruption. White dwarfs regularly show signs of having accreted rocky material from destroyed planetary bodies. If something from a disrupted planetary system is orbiting close to a white dwarf, it could produce the observed irregular flickering. The distinction between an intrinsic stellar process and an extrinsic orbiting object is difficult to make from brightness measurements alone. Spectroscopic observations looking for chemical signatures of accreted material, combined with precise timing analysis of the flickering, are the tools being used to distinguish the hypotheses. Dead stars, flickering for unknown reasons, surrounded by the remnants of destroyed worlds. Story 39, the South Pole Wall, a massive cosmic structure hidden behind our own galaxy that we only just found. One of the great frustrations of extragalactic astronomy is the zone of avoidance, the region of sky obscured by our own galaxy's disk and the dust and gas within it. About 20% of the sky is effectively blocked from optical observations by the Milky Way itself. Whatever large-scale structures lie behind our galaxy's disk are largely invisible to us. In 2020, astronomers announced the discovery of the South Pole Wall, an enormous concentration of galaxies extending across the southern celestial hemisphere that had been hidden behind the galactic plane. By using infrared observations and redshift surveys that can partially see through the galactic dust, they mapped a massive structure approximately 700 million light-years away that stretches for at least 1 billion light-years. The South Pole Wall appears comparable in scale to other known massive structures like the Great Wall, and comparable structures have been found to significantly influence the motions of nearby galaxies through gravity. The South Pole Wall's gravitational influence may be contributing to our own galaxy's peculiar velocity in ways that previous large-scale structure maps, which missed it, couldn't account for. We're still mapping the full extent of the South Pole Wall. Parts of it remain obscured by the galactic plane and can't be fully characterized. Its total mass and extent are still being determined. The specific unsettling implication: we've been trying to understand our galaxy's motion through space and the large-scale structure of the universe, while missing a significant chunk of what's pulling and pushing us. Our map has had a big blank spot for decades, and we've only just started filling it in. There may be other structures comparably hidden in the zone of avoidance. Story 40: Why Space Keeps Not Making Sense. What it means that 95% of the universe is still unknown. We've been through 39 space mysteries. Dark matter we can't detect. Dark energy we can't explain. 2 measurements of how fast the universe expands that disagree with each other. Giant radio circles with no confirmed source. A century of unidentified absorption lines in starlight, missing ordinary matter. An impossibly energetic particle from an unknown source. Fermi bubbles from a past event we haven't identified. Stars too massive to have formed. Black holes too big for their age. A background hum of gravitational waves from sources we're still determining. Galaxies that shouldn't exist yet. Planets floating free through space in numbers we didn't expect. Here's the specific thing this list reveals. Ordinary matter. The stuff made of protons and neutrons, the stuff you and every galaxy and every star are made of, accounts for about 5% of the universe's total mass energy content. The rest is dark matter and dark energy, neither of which we understand. We have a detailed, mathematically sophisticated, observationally tested model of the universe. The Standard Model of Cosmology, CDM, predicts the large-scale structure of the universe, the properties of the cosmic microwave background, the abundances of elements, and the overall evolution of the cosmos with extraordinary precision. It works extraordinarily well, and yet it contains 2 major components, dark matter and dark energy, that are entirely unexplained in terms of fundamental physics. And within the 5% of the universe that's ordinary matter, there are mysteries like the coronal heating problem, and the missing baryons and population 3 stars and FRBs and everything else on this list. The universe isn't keeping secrets from us on purpose. It's just very large and very old and governed by physics that our instruments and theories are still catching up to. Every mystery on this list has a real answer. We just haven't found it yet. The finding is the point. The fact that there's still this much to find is the most interesting thing of all.